Hello, 30-1s. Today's lesson is lesson 1 in your new unit, polynomials, and we're looking at the characteristics of polynomials. So what we're going to explore today is, what do the graphs look like in grade 12? Well, before we explore what the graphs look like in grade 12, what I want to do is go back and look at what the graphs look like in grade 10 and grade 11, because we can take the things that we learned from grade 10 and grade 11 and just transfer them to grade 12. So all the way back to grade 10. In grade 10, our graphs were rather basic. They were these nice linear graphs. So I was either increasing or I was decreasing. In grade 11, our graphs got a little bit more complicated, and we had these parabolas. And in grade 11, we usually describe these as saying the graph opens up or the graph opens down. So what will grade 12 look like? That's what we're doing today. Let's go back to grade 10 a little bit more. Okay, the equation of these two graphs in grade 10, we would have labeled as mx plus b. If I had my way, we wouldn't call it mx plus b. In fact, I would call it ax plus b. Here's why. In grade 11, we look at the general form of a quadratic, and how do we write it? We write it as ax squared plus bx plus c. So now grade 10 and grade 11, the equations look the same. So what did we have in grade 10? Well, this linear, what I want you to notice is that the highest exponent that we actually have is 1. And the highest exponent that we have in grade 11 is 2. So if you had to take a guess, what do you think the highest exponent we would have in grade 12 be? You got it. We are going to step it up a level, and we're going to go up to degree 3. And in fact, we're not going to just stop at degree 3. Our highest exponent will go beyond 3, but I'll talk a little bit more about that in a bit. So the highest exponent we see is known as the degree. The highest exponent. So grade 10, degree 1. Grade 11, degree 2. Grade 12 will be degree 3, degree 4, and degree 5. We won't go any further than degree 5. Now, in grade 10, a couple other things that we analyzed on our graph is we would have said, okay, what does our slope tell us about our graph? What does this initial number tell us about our graph? Well, in grade 10, we would have said, okay, if the slope was positive, our graph would have ended going up this way. And if our slope was negative, we would end going down. Same thing here. If my lead coefficient was positive, we would have said this graph would have ended up. And if the a value was negative, it would have ended going down. So the a value will be the same for us in grade 12. This is known as the lead coefficient. The lead coefficient tells us how a graph will end. Perfect. Okay, so those were some of the things that we focused on. Another thing that we focused on in grade 10 and grade 11 was this term here. In grade 10, we would have said this is your slope y-intercept form. So the b value would have been your y-intercept. In grade 11, I would look at that value, the c, and I'd say, that's my y-intercept. So guess what? In grade 12, that d value will be your y-intercept. This has a better name. This is known as the constant term. constant because it doesn't have a variable, so it's not changing. So the constant term tells us our y-intercept of our graph. Okay. Now, to see what our graphs are going to look like in grade 12, I want to talk about turning points. Let's look at our graphs from grade 10. How many times do our graphs from grade 10 turn? Well, they're linear. They're constant. They don't turn anywhere. In grade 11, with our parabola, how many times do our graphs turn? Well, I can see that they both turn once. They would turn maybe here, and the other one would turn here. So I would say one turning point. So if in grade 10 we had 0 turning points, and if in grade 11 we had 1 turning point, in grade 12 maybe you're thinking we should then have, oh, maybe you just said 2 turning points. Perfect. Here's what our graphs are going to look like in grade 12. 2 turning points. 2 turning points. In fact, as we get into degree 4 and degree 5, we might see a couple more turning points. Okay, so that's important. So how do I know my turning points by looking at the equation? So degree 1, 0 turning points. Degree 2, 1 turning point. Degree 3, 2 turning points. I don't have it drawn down, but if I was to say to you, I'm looking at degree 4, guess how many turning points you might see? 3. So the number of turning points is 1 less than the degree. Simple as that. Now, I want to give that a slightly better term than turning points. We're going to refer to these turning points as relative maximums, relative maxes, or relative mins. All right. So turning point is kind of a bit of a heuristic definition. I can look at it and say, yeah, that's where my graph turns around. The proper term is relative max or relative min. Okay, so friends, what we need to do here is we need to, given a graph, we should be able to hopefully make the equation, or given the equation, we should be able to make the graph. That's what we're trying to do. And so how we're going to do that is we're going to talk about the degree, the lead coefficient, the constant term, how many turning points there are, and we almost have this already. Okay, so let's take a look at a question. Let's say, for instance, I give you something like this. Okay, a graph from grade 11. So nothing too crazy, just a nice graph from grade 11. So here's how I'm going to analyze this now. The first thing I'm going to say to myself is, what is the degree of this? Well, the degree of this is degree 2. Another way to say that is that this is an even degree. You'll see why that's important in just a couple minutes. Then I'm going to say to myself, how does the graph end? Well, to find that, I look at the lead coefficient. The lead coefficient is positive. So that tells me my graph will end up. Okay, so then my question is, how does my graph start? Well, think about what we remember from grade 11. From grade 11, our parabolas either look like that or like that. So an even function always starts and ends going the same direction. An even function starts and ends going the same direction. So if this is an even graph, if I end going up, I'm going to start by going up. So this graph will go up, up. Perfect. Okay, so there's where that little piece about the even or the odd degree will come into play. That's how it's going to help us figure out how our graph begins. Okay, so I could also say, what does my constant term tell me? Well, my constant term is -6. Well, what that's telling me is my y-intercept. My y-intercept is at 0, -6. Wow, we actually have a lot of information here. We know how our graph ends. We know how our graph starts. We know where the y-intercept is. How many turning points do we have? Well, if we're degree 2, that means we have one less turning point than our degree. We will have one turn. In this case, we'll have one relative minimum. Now, with all of that information, here's the fantastic piece. We should be able to roughly draw what this graph will look like. So here's my Cartesian plane. And I'm going to use the information that I was just able to figure out to help me draw this. So my graph ends going up. So I'm going to put an arrow up here. It's even, so it starts and ends going the same way. So I'll have another arrow over here in quadrant 2. I've got a y-intercept somewhere down here at -6. And here's what I know. It has one turning point. So this graph is going to do something more or less like this. Now, my graph's not perfect. If I pulled out my graphing calculator, it'll have a similar shape. That's what I'm going for here. I should have a general idea of what the shape of this graph looks like. Down here, to find my relative minimum, the only way you are going to be able to tell me where that is by using your graphing calculator. You won't be able to figure out that graph algebraically until you're in calculus. Okay, if I wanted to find my x-intercepts, guess what we're going to do? To find our x-intercepts, we are going to factor. So this is why factoring was so important in grade 10 and grade 11, because we're going to keep using that skill over and over and over again. So let's find our x-intercepts. Well, all we need to do is factor this thing. So if I want my x-intercepts, I'm going to let y equal 0, and I'll factor this. Well, the first thing I notice is that I can divide everything by 2. And now I should be able to factor this thing. So x plus 3, x minus 1. So therefore, x is equal to -3 and 1. So there's -3, there's 1. And my x-intercepts I should always write as a coordinate pair. Okay. Geez, we just did a really good job of graphing that without touching a graphing calculator. That's what we're trying to do here, is to try to analyze graphs without touching our graphing calculator. Okay, now Let's do this one more time. That was a grade 11 function. Let's jump ahead to a grade 12 function. So for our grade 12 function, again, we will be able to go all the way up to degree 5 by the time you're done today's lesson. But for now, let's just look at degree 3, also known as a cubic. So when I go to analyze this thing, I'm just going to keep asking myself the same questions. What is the degree of my function? Degree is the highest exponent I see. This is degree 3. Also, it is odd. Perfect. What is my lead coefficient? Well, my lead coefficient is what's in front of my highest term, so it's 1. It's positive, which means the graph ends up. How does my graph begin? How does my graph start then? Well, if you think back to grade 10, when we had an odd degree, our graph started and ended beginning opposite directions. So we're the same thing here. This is degree 3. So guess what? If our graph ends going up, it's going to begin going the opposite direction. It's going to go down. Okay, so odd functions go in opposite directions. They go down, up, or up, down. All right, so now we've got that. How many turning points will we have? How many relative maxes or mins is the better thing to say? Well, we're degree 3, so my number of turning points is 1 less. I will have 2 turns, or 2 relative maxima. Perfect. Okay, constant term is our y-intercept. So our y-intercept is at 0, -3. Okay, friends, guess what? We should be able to roughly draw this thing. Cartesian, right there. Okay, so our graph ends going up. Perfect. I'm going to put an arrow somewhere up here. It's odd, so it starts and ends the opposite direction. I'm going to put an arrow down here somewhere. Now, I have a y-intercept at -3, so there's that. Now, I don't know my x-intercepts, but for now, I'm just going to take a shot at what the general shape of this would look like. I need to come up. I'm going to have to turn around somewhere. And I'm going to have to turn back around and go through that y-intercept. Maybe it looks just like that. Okay, again, my graph isn't perfect. That's not what I'm shooting for at this moment. At this moment, I'm trying to get the general shape of my graph. Okay, what about our x-intercepts? It looks like we should have 3 of them. So how did we find our x-intercepts in grade 11? Well, we let y equal 0. Let's try the same thing here. We're in grade 12. Let's try the same thing here. So if I want to find my x-intercept, I try to let y equal 0. Okay, wait a minute. How are we going to factor a cubic function? All right, we're going to have to learn something new. That's what's going to happen over your next couple lessons when we start talking about the remainder theorem and the factor theorem. So that'll be a little bit involved. Okay, you're going to learn a new way to factor something like this. So for now, we won't be able to factor this. We will learn how to factor this soon. All right, so that's it. For now, all I can say is there's the general shape of my graph. And again, The only way I expect you to tell me where the relative max and the relative min are is by using my graphing calculator. Until calculus, that's as good as it gets. That's it, my friends. You can now, given a function, come up with a pretty darn good shape of the graph. Perfect. There's 1/2 of your first lesson done. In the lesson, it will expand into degree 4 and degree 5. To look at those just a touch more, what if I gave you this? Let's go -2, x minus 3 squared, x plus 1, and x minus 2 squared. Okay. So notice the difference between this function and the previous two that I've drawn for you. This is in factored form already. Back here, we couldn't factor this yet. But if something's factored already, it's beautiful. We already know the x-intercepts. So same question, we're going to graph this thing. Before we do, let's analyze it. Degree. To find the degree of a factored function like this, what I'm going to do is I am going to add the exponents on each of our factors. Because if we multiplied this out, that would give us our highest degree. So 2 plus 1 plus 2 is 5. This is degree 5. This is the highest degree that I can give you in grade 12. It's also odd. Now, how many turning points will we have then? Okay, this is where it's going to start to get a little bit trickier, because now we're in degree 5. Well, we should have one less than the degree, so we should have 4 terms. Excellent. Now, our lead coefficient is positive, is negative. So this graph will end down. How do we begin? Well, we're odd and we end down. Odd graphs start and end going opposite directions. So this will start going up, like that. Okay, constant term. Well, I can't see the constant term very easily. It's in factored form. So what we could do is simply let x be 0. That would give us our y-intercept. Okay, so I'm not going to call it the constant term because I can't see it. I'm going to call it the y-intercept. So I'm going to let x equal 0. So what do we get? Sub in x is 0 and simplify. And so we will get a nice negative number here of negative 72. So our y-intercept is at 0, comma, negative 72. Okay, it's way down on our graph. Now, our x-intercepts, it's in factored form, so I can actually already see our x-intercepts. Our x-intercepts are, I'll write it up here, our x-ins, well, it's already factored. So there's an x-intercept right there at 3, 0. There's another x-intercept right there at negative 1, 0. And our last x-intercept is right there at 2, 0. Lovely. That's the best part about having something factored. If something's factored, we immediately know the x-intercepts. Okay, let's see if we can draw this thing. Okay, so what do we know? We know our x-intercepts. So we've got an x-intercept over here at 3. We have a next x-intercept at 2. and we have another x-intercept over here at -1. Our y-intercept is way down here at -72. Okay, now our graph ends going down, so there's going to be an arrow somewhere down here. It's odd, so it starts and ends going the same way. So we've got another arrow up here. Now, how is this thing going to look? Okay, this is the last piece of graphing that I really need you to know. What we need to do is we need to come back to our function that's factored, and we're going to look at the exponents on each of our factors. This is known as the multiplicity. So the exponents on each of our factors will be called the multiplicity. Well, here's what's going to happen. I'm going to look first at the x-intercept of -1. So I'm looking at this one here. So the exponent is 1. So think of grade 10. When the exponent was 1 on your graph just kept going, right? It was a straight line. It just kept going. That's what's going to happen here. When I say keep going, I'm going to say what's happening at the x-axis. It's going to come straight through that graph. Perfect. Now it's going to have to, I'm going to draw that just so it's a little straighter. Okay, so it's going to come straight through my graph, something like that. Okay, now it's going to come down. This graph has to turn around somewhere. We've got this crazy point. Maybe it turns around the y-intercept. Again, I don't really know, but it does have to turn around. That much I do know, because it has to come back up to the x-axis. Okay, so now we're coming up to the x-intercept of 2. So I'm going to go and look at my multiplicity where I would get that x-intercept of 2. The multiplicity is 2. Think of grade 11. When we had a degree of 2, we ended up getting a parabola. Same sort of idea here. We're going to come up to the x-axis. We are going to come to our x-intercept, and we're going to hit the x-intercept and bounce off. I'll give you a better term for that in a second. But for now, when we have a multiplicity of 2, we're going to bounce. Okay, well, I'm going to start coming back down. But I know I've got to turn back up around again because I've got to get back to that x-intercept of 3. So somewhere there's going to be a relative min. We're going to come back up, getting close to that x-intercept of 3. So I go and look at the multiplicity on the factor that would give me that x-intercept. And guess what? It's a multiplicity of 2. So I again think of grade 11. I'm going to turn around and look at, there it is right there. It hits the x-axis and it bounces. And now it's going to turn back around just like that. So again, I know if I picked up my graphing calculator and plug this thing in properly, it's not going to be 100% perfect. I don't know for certain where my relative mins and maxes are, but again, the general shape of our graph will be correct. So the last piece that we just looked at here were these exponents on our factors. This is known as the multiplicity. So the multiplicity. This is how it works. So if I had a factor of x plus 2 to the exponent 1, so my multiplicity is 1. So a multiplicity of 1. What your graph does is it just goes straight through the x-axis. So your graph will pass through the x-intercept. If I had a factor of x minus 4 squared, so I would have multiplicity 2. What's going to happen when I drew this graph here, I said, okay, it comes up to the x-axis and it bounces. Okay, that's kind of what it looks like it's doing, but I need you to know the proper term for that. it touches the x-axis and it bounces off. The proper term is this is a point of tangency. If you want to think of it in your own mind as bouncing, that's fine. Bounces off. But don't ever write that on a test. Now, we've got one more multiplicity we have to consider here. It's when we have a multiplicity of 3. Now, a multiplicity of 3 is a little bit tricky to draw. So what this does is it looks very much, again, like a cubic function. A cubic function looks something like this, right? Or something like this. It's the graphs that we explored earlier on. So when we have a multiplicity of 3, what will end up happening, how we describe this, is our graph changes concavity. So the graph will change from concave down to concave up, or it will change from concave up to concave down. So let's see if we can draw one of these. So I give us the function x minus 5 cubed, x plus 3 to the exponent 1, x minus plus 6 to the exponent 2. Now, this is actually degree 6. 3 plus 1 plus 2, which is 6. Now, that's technically beyond what we have to do in 30-1, but I just want to do it because it doesn't matter. The rules are all the same. Lead coefficient is negative, so the graph ends down. How does it begin? Well, we're even. We end down. An even graph starts and begins the same way. So we will also begin down. Perfect. We know our x-intercepts because we're in factored form. Our y-intercept we could find by letting our x values be 0, but I'll leave that off for now. Let's see if we can get a rough shape of this graph. Well, I know my x-intercepts, so I'm going to label them. We've got one over here at 5, right there. We have another one at -3. And our first one at -6, right there. Okay, let's see if we can get a rough shape of this graph. So the graph ends going down. So there's going to be an arrow somewhere down here. It's even, so it begins and ends the same way. So there's another arrow over here. Okay, now all we're going to do is go from left to right and analyze what happens at each of these x-intercepts by looking at the multiplicity of the factors. So the first one is at -6. So that's this factor right here. The multiplicity is 2. So the graph will come up to the x-axis and it hits the x-axis and bounces off. Correct term, there is a point of tangency there. Our graph comes down. It has to turn back around somewhere, so a relative min. I don't know where that is. That's called calculus. I come back up to my next x-intercept. I'm coming up to -3. I look at the multiplicity. The multiplicity is 1. So I think of grade 10. I'm just going to keep going straight through. I have to turn back around because I have to get to that other x-intercept. I don't know where she does it, but she does. She turns back around. I'm coming towards an x-intercept of 5. So I look at my multiplicity. That's a multiplicity of 3. So this multiplicity is where our graph changes concavity. Now, this is a little tricky to draw. Okay? So what you want to try to accentuate is that it's got a bit of that cubic function look to it. So it's a little tricky to draw, but if you can kind of see there, I just changed concavity just a slight bit. And so now I went to concave, from concave down to concave up, and there's where my graph is going to end. Okay, so that's what we're going to do. So technically degree 6 is beyond 30-1, but we just drew one. Works the same. Okay, so what we looked at here today, we talked about the degree, the highest exponent we had. It tells us how our graph is going to end and begin by analyzing the lead coefficient and the degree. The constant term is the term at the end of our function if it's not factored. That constant term is the y-intercept. So if I was looking at this graph here, the y-intercept is right there. That would tell me that my constant term is positive. All right. And once we know our x-intercepts, we can look at the multiplicity. It's going to help us talk about the behavior, draw the behavior as our graph gets close to those x-intercepts. Awesome. Again, relative min, relative max. I'm going to use my calculator. All right, we are almost done. I'm going to do one last example, and you are set up for this lesson. Guess what? If I can give you the function and you can make me the graph, then I need you to be able to go the other way. So I'm going to draw us a pretty graph. There, she's gorgeous. I'm going to say there's an x-intercept over here at, I don't know, -7. I'm going to put our other x-intercept right here. I'm actually going to put it right at the origin. And let's see if we can make the equation of this function. I'm going to analyze it the exact same way I would if I was given the function. First thing I want to notice is, what's the degree? Well, to analyze the degree, I'm going to look at the x-intercepts. Look at this x-intercept over here at -7. Well, can you see that this is a change in concavity? So that means the multiplicity rate here has to be 3. The multiplicity is 3 there. Then I come to this x-intercept. And I say, what's happening at that x-intercept? Well, I see my graph hits the x-axis and bounces. It's tangent at the x-axis. That means the multiplicity is 2. So what's the degree of the graph? Well, the degree of the graph then will be 3 plus 2, which is 5. So the graph is also odd degree, which makes sense because looking at the graph, I see that it starts and ends going in different directions. Okay, what's my lead coefficient going to be? Well, the graph ends going up. So that means the lead coefficient must be positive. Well, let's see if we can dummy up an equation here. So we have an x-intercept at -7. So that's x plus 7 as a factor. We have an x-intercept at 0. Well, that's just x. Now, let's get the multiplicities involved. At -7, we had a multiplicity of 3. So guess what? There's our 3. Now, at 0, at the origin, we had a multiplicity of 2. Right there, x squared. And the lead coefficient is positive. Now, we're very close to being able to finish this off. There's one thing that I really need you to notice and to pay attention to when you're doing this in your lessons and on your test. We must always remember and say to ourselves, is there a vertical stretch? That's what that lead coefficient is also telling us. It's a vertical stretch. So what I'm going to do here, it's a very easy thing to forget. I'm going to put an A there. That's my vertical stretch. It's my lead coefficient. Okay, well, how would I find that A value? Well, to find A, I'm going to have to sub in another point. So there will be another point labeled on my graph here. I don't know, let's say that's at 3, 6. So if I want to find what A is, I'm going to sub in another point. So I sub that into our function. This will be 3 squared, 10 cubed. So we're going to get some big numbers because I made a crazy graph here. So this is 9, 1,000. So that's 9,000 times A. So A is equal to 6 over 9,000, which should reduce to 2 over 3,000, oops, which reduces one more time to 1 over 1,500. Make sure we've actually answered the question. I want to know what the equation of this function is. So let's write that equation. Here we go. A value, 1 over 1,500. X squared, x plus 7 cubed. And there it is. Of course, at this point, I would go back and I would graph my function to make sure that it looked exactly like that graph and that the points that I was given are on the function that I've made. Okay, that's it, my friends. You are now able to analyze a graph and create the function. Or vice versa, given the function, you should be able to draw me a rough shape of the graph. That's it. There's your first lesson. Hope that helped. Good luck. Enjoy the lesson.